So the homology classes are defined by the modulo of these two sets, where ZP is set of all P chains. So let's say alpha P, which don't have a boundary, and BP is set of all P chains which can be written as a boundary of some one-dimensional higher chains, which is P plus 1 in this case. Now, in case of torus, if we take T2, so let's see about, what is the H1, which is the one homology. So the possible one chains which are without boundary are these circles basically, and then the other ones are which kind of enclose this bigger hole. So these, let me call this, let's say C and A and B. So the statement of the homology is that this A and B are equal or equivalent because they are kind of related by this boundary of this inner surface we have here. So let me call it sigma. Then A can be written as B plus del of sigma. But A and C or B and C are not in the same cohomology class because you cannot have any two-dimensional manifold, submanifold here which can kind of relate this cycle to the bigger cycle here. Okay, does that make sense? We can take another example for, let's say, S2. So for S2, okay, so let me just write that H1 of T2 over R, where R is denoting what we are taking the coefficients of the chains to be. So AP was kind of given by this formal sum where Ci and I. So this Ci we are taking to be real number here. So H1 is because we have kind of two different type of cycle. It's like R plus R, and H0 for torus is just R because it's kind of collection of all points. The zero cycles here are the points on the torus, and H2 will again be R because we are taking the whole torus only. The only possible two cycle which doesn't have a boundary is the torus itself. Okay. Now in case of sphere, H0 is same because again we are taking all the collection of points. So it's just R, and H1 is 0. Why? Because all the cycles which don't have a boundary can be written as boundary of some two-dimensional surface. For example, if we take this circle here, I can write it as the boundary of either this hemisphere or the bottom one. So any one cycle can be written as the boundary of a higher dimensional chain. So basically what we have is that this ZP is 0, all the chains lie in the BP. So that's why this H1 of S2R is 0, and then H2 is again trivial because we are taking the whole sphere which is boundaryless itself. Okay. So in general for Sn, only H0 and Hn are R, and all other homology classes are kind of empty. So this is Okay. Yes. So for example, 2 torus, if we take this is T3, so there will be one cycle here, okay, and then here and here. So it will be like 4 classes. The total H1 will be given by R plus R 4 times, because these cannot be, deformed into one another by taking some boundary of some 2 dimensions. Okay. Now we have the homology. We can define the dual space, vector space, to that, which is called D-Ram cohomology. Okay. So HP. Okay, so all these should be lower, because homology I am denoting by lower scripts. So the cohomology where H superscript P DRAM of a manifold M over real numbers is given by similar definition, and here ZP is basically set of all P forms which are closed, and you can guess BP will be given by all P forms which are kind of exact. So you can write it as D of some lower form, let's say alpha P minus 1. Okay. So similar to the previous case, omega and omega prime are equivalent to each other if we can write omega prime as omega P, let's say P form, plus D of some alpha P minus 1. Now we can take the same example of torus. So T2 is basically S1 cross S1, and let's say the coordinate of this circle is theta 1 and this circle is theta 2. Then all possible 1 forms we have are d theta 1 and d theta 2, okay, which cannot be written in that form. So basically the dimension of H1 T2 is 2, and only one closed form exists, which is all other will be dependent on this. So that is this d theta 1 wedge d theta 2. So the dimension of H2 T2 is again 1, and the 0 form is just some constant. So the dimension of H0 of T2 is again 1.
So these are upper index 0.
Yeah, right, right. Thank you. Yeah.
Can I ask?
Yes.
How exactly did you compute them? I didn't quite follow the H0, H1, H2.
Okay. So H0 is like if you take 0 cycles, which will be
Cycle here is in the definition. What
cycle is all the chains which don't have a boundary.
Okay, okay.
So it's just points on any manifold for 0.
But points will never be a boundary of anything, right?
Yes,
pair
that
of points will only be boundary.
yes,
of something.
yes.
Okay.
So one point you can take always.
Huh.
That's why it's just R. Any point you can take.
But I thought H0 is Z0 by D0, and Z0 quotient D0, right?
Yes.
Z0 is 0, right? But
Why?
I don't. I mean,
We can take one.
point, but one point will never be boundary of anything, right?
Yeah, that is what we want, right? Because the p cycles which are boundary of something are basically lie in BP, not in.
I see. Okay. And why is dou of the point 0? That doesn't.
Okay, I mean, does point have a boundary? I don't know. Is that?
Intuitively, I understand.
Yeah, but I mean, that is the way only I understand.
Okay.
You just define it like for self-consistent definition, you define that boundary of a point is 0.
Dou of point is 0.
Okay. And then is it okay? The 1 and 2.
And 1, so basically the same way the set of all one chains.
1 cycles, which are basically chains without boundary.
Right.
So those will be these circles. And these two are related, only the different, the bigger one and the smaller one. So there is R plus R.
Okay.
So for sphere,
Is it R or is it just 0 to pi or something like I mean, so if I give a cycle, then I have
0 to pi is like R, a segment of, a line can be mapped to.
so for the sphere, this H1 is 0 because as you said that every circle is like a boundary of something.
Yes.
But total it's like going and coming back, so it's not like a boundary.
Yes.
It's just going and coming back. So
Yes, it is not a boundary of anything. Is that okay? Should I prove?
and the second coefficient, what does that mean? The semicolon R in both cases?
In that case, it meant that we are taking the CIs to be real numbers. In this case,
Does that make a difference? I mean, if I keep M the same, but just changing R to C or R, does it change the?
yeah, instead of R, then it will become Z or C, whatever the number is taking. Okay. So now the last, or maybe second last again. So there is a kind of isomorphism between harmonic forms and DRAM cohomology. So let's take M, which is a manifold, a compact manifold without boundary. then only we can do the Hodge decomposition. So in this case, any P form basically can be written as some d of alpha p minus 1 plus d dagger beta p plus 1 and a harmonic form gamma p. So this is a closed form and co-closed, and this one is the harmonic form. And just to remind that harmonic forms satisfy this condition that d of them and d dagger of them are 0. Okay. So the cohomology are a set of such P forms for which are closed. So if we take d of omega p to be 0,
How long more will you take? There is some issue with changing the
oh is it? So just maybe maximum 10 minutes I think.
Do we have 10 minutes?
I guess.
So if we take d of omega p to be 0, one can check that this implies that d dagger of beta p plus 1 is 0. Again you have to take the inner product of, let's say, d of omega p with this d dagger of beta p plus 1 and check the positivity condition for that. And given that this implies that d dagger beta p plus 1 is 0, we can write omega p as d of alpha p minus 1 plus gamma p. But this is again the definition of the cohomology equivalence classes. So that means that basically omega p is equivalent to gamma p, or maybe they belong to same cohomology. So Hp of m. Okay. Now if we take the other condition that we have to have omega p harmonic, then the d dagger of omega p should also vanish, and that will simply imply, using the same logic, that d of alpha p minus 1 is 0. So basically omega p is equal to gamma p, and this is nothing but a statement of isomorphism for Hp, which is the P cohomology class, to the kind of space of the harmonic. So I'm just writing HARM for. So I want to prove that for each cohomology class there is a representative which is the harmonic form. Okay. So the cohomology class is defined as, like, let's say the first thing is that you have to have the form which is closed. So we can write any P form in terms of this using the Hodge decomposition. Then we impose that d of this omega p is 0. Okay, that will give me that d dagger of beta p plus 1 0. So now we have omega p as some d of some p minus 1 form plus 1 harmonic form. Okay, so basically that means omega p and gamma p belong to same cohomology class. Okay. Now let's say if I assume that, just to say that if we take any p harmonic form, then it will be basically be equal to the gamma p itself. So we only have cohomologically. So so if we take d dagger of omega p 0, then using the same argument we arrive that omega p is equal to gamma p. Does that make sense?
Why is d dagger of beta 0? D of d dagger is 0. D dagger of beta is 0.
Yeah.
Then how do you get that d dagger is 0?
I think so. Let me just write it here. So if we take d omega p That means that this is 0, this is 0.
Yes.
We are left with d of d dagger of beta p plus 1. Right?
Yes. And you think this is 0?
No, yeah. So this is 0 for this to satisfy. Okay. Now I can take, I think, omega p, or let me, maybe not this, beta p plus 1 and the d dagger of beta p plus 1, the inner product of this thing.
Okay.
Okay. So this is 0, right?
Yes, that is 0. Yes.
So this will be equal to 0.
Right.
Now I can use the the duality, which d going there will be d dagger. So it's d dagger beta p plus 1, d dagger beta p plus 1, that is equal to 0. So this is kind of a norm of form. So when you, then it should be 0 if the norm is 0.
But this is an extra condition that you impose, right?
Yeah, we can, if you are okay with this much, then yeah, we can. Just to say that there is a isomorphism between the harmonic forms and the cohomology classes. Maybe.
So the harmonic is like the Laplacian acting on it is 0, right?
Yes.
So then how did you get this?
The Laplacian acting on 0 is equivalent to these two things, right?
But this is more constant.
No.
So that always implies this.
Yes. If and only if we have this condition, then the Laplacian will vanish. Do you want me to show that, or?
Because even a positive definite operator, like d dagger is d plus d dagger the whole square. That
Yes.
means that if that is 0, then d plus d dagger are acting on it.
Yeah, it is very simple. If I take the inner product of these two, then delta is dd dagger plus d dagger d, right? And that will be equal to d omega plus d dagger omega d dagger omega. And if this is 0, that means this should be 0. That means these two should individually vanish. Okay, so we have a kind of a maybe isomorphism HP of MR, same as isomorphic to the set of harmonic P forms on same manifold, comma R.
Sorry, why you are putting this condition g of omega p and d dagger of omega p equal to 0? If you put this condition, that is the condition for this harmonic form, right?
Yes.
Then like isn't it trivial that omega p is equal to 1?
Yes. So I just Sorry.
You want to
So
find the harmonic form.
yeah, we can just I want to kind of find the harmonic form, but we can just stop here also.
So two harmonic forms cannot belong to the same thing.
Yes, they are equivalent basically, or same, you can say. Okay. Now, I don't know if I should cover this one. Okay, let's skip it. So, one more definition, which is what we have been doing all day.
Can I ask another question?
Yeah.
So how you have the chain in the D's? The DRAM homology is in the D's, right?
Yes,
Exterior
yes.
data. Is there something analogous in D daggers? Some other type of homology?
I don't know, but
Like you are doing closed modulo exact. Is there something like closed modulo co-exact?
I don't know. So, I mean, it looks like there should be, but I don't know what it is called. Okay. So we can define inner product of a p cycle which belongs to Zp, and so basically definition of cycle is that it should belong to Zp and a closed p form which is belonging to the Zp of DRAM as pi of Cp comma omega p equal to, so basically we are integrating this p form over this p cycles which are like p dimensional manifolds, and these omega p's are called periods. Okay. And we are able to do that because let us say if I take some omega p plus d alpha p minus 1, which is kind of similar to omega, then the integration of this Cp d omega plus d alpha p minus 1 we can write as the p plus integration over Cp d alpha p minus 1. Now using the Stokes theorem we can, so Cp omega p plus, we can integrate the alpha p minus 1 over the boundary of this p cycle, but the boundary of p cycle by definition 0. Okay. So for in that sense, for every Cp there is kind of a omega p for which you can define this. It is related to what we call this DRAM theorems, which I am not going to do here. Just for the future thing that we can define periods which are basically integration of some p form over some p cycles.
You use Stokes theorem to define this, is it?
Yes.
Stokes theorem people prove using these things, using some duality between homology and cohomology. I could be wrong. I just thought it.
I don't, maybe, but in Iguchi I think it is done this way. So okay, so the last thing is when we are compactifying the string theory from 10 to 4D, what we do is we take 3-dimensional complex manifold instead of real manifold. So 3-dimensional complex manifold is kind of equivalent to 6-dimensional real manifolds. So we need to see these things in the complex manifold. So on a complex manifold, one form can be written as, so omega z bar, this is let us say one form, equal to omega some z bar, the component I dzi plus omega z bar some component j bar d bar j bar, and I will denote these two as omega 1 comma 0 plus omega 0, comma 1. So the first, term inside the bracket is kind of giving us how many holomorphic indices are there, and the second one will give anti-holomorphic. Sorry. Yeah. And given that, we can basically decompose any K form into this P, comma Q, complex forms. So we can have any, let's say, P form written as sum of omega r comma s, where r plus s equal to P. Okay, this is easy to see if you define your zi's to be kind of xi plus iy, yi's, and z bar same thing with the minus sign. Okay. Now, in this notation, our exterior derivative is given in terms of this sum of two derivatives, which is, this is kind of dzi del del zi, and this is dz bar I del z bar I bar. Okay. So you can guess that this del basically takes P comma Q form to P plus 1 comma Q form, and del bar takes P comma Q form to P comma Q plus 1 form. Now, similar to the previous case, we can define a cohomology in this case as well. And that is what we call Duval cohomology. So H P comma Q is given as all omegas P comma Q which are closed over this anti-holomorphic exterior derivative, and similar to the previous case, modulo omega P comma Q forms which can be written as some derivative of alpha P Q minus 1. Now, in this case, we are only taking this del bar cohomology because that is kind of what we want. So basically, when we talk about complex manifold, the transition functions should be holomorphic and the vector bundles also should be holomorphic. So because of that, we can take we are taking this del bar. We can have a del cohomology as well, but physically, I mean, it is not important to us. Now, on a compact and scalar manifold, so we will see what these scalar manifolds are tomorrow when we will talk about Calabi-Yau manifold. I am just defining something. So, on compact scalar manifold, any this DRAM cohomology over some complex field can be written as direct sum of these, P comma Q Duval cohomology, and the dimension of these H P comma Q are what we call Hodge numbers, which is H P comma Q. And yeah. And these are related to the Betti numbers, which I should have defined. So the dimension of this cohomology, so dimension of DRAM cohomology are called Betti numbers, and the Euler characteristic of a manifold is given by this graded sum of these Betti numbers. So that will be kind of important later. This is the last thing. So yeah, so in this case BP can be written as sum over RS R plus S equal to P, these Hodge numbers R comma S. Okay, and just one more minute. So due to Poincare duality, this H R comma S is same as H D minus R, sorry, D minus S, where we are talking about d-dimensional manifold, and due to complex conjugation, H R comma S is same as H S comma R. So this is only defined on the Kähler manifold where we can have a kind of Hermitian metric. So we'll talk about it later. And for any complex manifold, we can have Hodge diamond. So let's say D equal to 2, then H0 comma 0, H1 comma 0, H0 comma 1. Then we can have H2 comma 0, H1 comma 1, H0 comma 2, and then H2 comma 1, H1 comma 2, H2 comma 2. So this is all possible, Hodge numbers we can have for any two-dimensional complex manifold, and we will see that these, first of all, these are related by these two kind of dualities. That's why kind of a diamond structure we have given. But also there is another symmetry called mirror symmetry, which is evident in Calabi-Yau manifolds, and we'll see that because of these dualities, not all of them are independent. Only the independent ones for the three-dimensional Calabi-Yau manifolds will be H1 comma 1 and H1 comma 2, and we'll see these are exactly the parameters which give us how many moduli fields will be there for a compactified Calabi-Yau manifold. So now it's done. No questions?
These are functions of both, right?
Yeah, but the
Yeah, I understand in what sense you're saying.
Yeah,
These
yeah.
are functions of both.
Yeah. Because if you kind of think of z's as x plus iy, then you can take any p form which is kind of dx1 to dx wedge product dx ip. The components will kind of split in these two when you write. So that is why they are form of function of both z and z bar.
The I0, 1, 0 is a function of both z and z bar.
Yeah, the component of it is function of that is what I was.
Kajal, what did you say about H11 and H12? They will be related to the.
Okay, so these will be only independent Hodge numbers for Calabi-Yau manifold, and we will see that H11 is kind of the number of Kähler moduli we have. We'll see what Kähler moduli are, and H12 are basically the number of complex structure moduli we have for Calabi-Yau manifold when we compactify.
Okay, so there are two kinds of moduli.
Yes.
Kähler moduli is for H11 and.
Yes, and there is also dilaton, which we'll see it tomorrow when I write the kind of field content of type 2B string theory. We'll see how these come.
Kajal, so these two conditions, H R is equal to the H of D minus R into D minus R and 7. These are true for any manifold or this Kähler manifold?
No, this is basically because of the Poincare duality, because these P forms are P tensor fields, right? So the number of independent components will be n factorial, p factorial, n minus p factorial. Okay. So where n is let's say D. So if you just change D to D minus P, the components are same. So kind of similar vector spaces.
So there's some physics reason why you're not considering the dou cohomology, is it? Like,
Yeah. So I'm not very clear about it, but if we take that, the yeah del instead of del bar, what it will do is kind of trivialize the whole manifold in some sense. So the non-trivialization of manifold is kind of related to this del bar. Maybe I'll find a a more better statement. Right now I don't have.
But at least up until this point, the holomorphic and antiholomorphic parts look similar.
Yeah. I mean, there is a theorem basically that if you say that some function which satisfies del of, is 0, harmonic in this, then it will be harmonic in del and del bar as well. So in that sense, they are kind of, we can have a cohomology corresponding to del, but I don't have right now a reason why we are not taking that. And I think the dimensionality are also same.
you will only be looking at Kähler forms, or
Kähler forms, sorry.
as in so the cohomology is for any P comma Q form, right?
Yes,
So you will have P equal to Q for Kähler, right?
yes.
So you will be only looking at those, and you will be looking at all sorts of.
No, we'll be only looking at which are relevant to kind of moduli fields corresponding to the compactified metric. So in case of Kähler manifold, we have metric which will have component like GAB and GAB bar. Okay, so corresponding to that, the this corresponds to kind of 1,1 form, the cohomology class of that, and this is kind of correspond to 1,2 or 2,1, whatever you want to call. And so the number of moduli fields will be related. I mean, they are exactly equal to these numbers. So we'll be looking on those two. Okay.
So if I were to instead consider only like the dou cohomology, I would look like 1,1 and 2,1, is it?
I mean, it will have all kind of, and 1,2 and 2,1 are same basically because
Right.
of this. So yeah. I don't know how to close this.